Alright, welcome back. So, this is episode 2 of my Homebrew 16-bit CPU that we are working on here. So, if you didn't catch the last episode, which was the very first episode, we put together this little circuit here that stores a 16-bit address in this register right here. Every single cycle, it is clocked and incremented by 2, and the current value is used as the address into a pair of ROMs here that represent program memory. And the data fetched from program memory is interpreted as an instruction and is stored into this IR, this instruction register. And the instruction register is now currently the input to the decode stage of the CPU, which is what we're kind of going to work on today, except we might kind of skip the decode, or well, there's different ways to go about it, I guess. So sometimes you'll see the CPUs will, from an academic sense, I don't have industry experience, but you could kind of consider operand fetching, so like getting values out of the register file for executing on. You can consider that to be part of the decode stage, or it could be part of the execute stage, or it could be its own stage between instruction decode and execute. We're gonna say for now that operand fetching is part of the instruction decode stage. So to that effect, yes, we're gonna work a little bit on the decode stage today. But just a quick demonstration. You can see right now the program counter is at 0. I clock it. Program counter is incremented by 2. Clock it again, incremented by 4. And you can see that as I increment the program counter, the value in the instruction register is also increasing. And then you'll see, I think after the program counter passes F, the instruction register will go to 0. Yep. And that is because if you look at the ROMs here, I've put a small program in memory here that just puts the values 1 through 15 in the first 15 addresses here, and after that it's all zeros, which is why the instruction register just dropped down to 0 after all of that. Now, of course, right now these instructions, they don't mean anything, they don't do anything, but that's just to demonstrate that we were walking through memory there. So yeah. So we're gonna start by adding a register file, which is funny, it's actually under the RAM menu here. Here it is. And there's significantly more ports on this device than there are on any of the other devices we've used so far. But basically what this is we can configure it. You can see data bits, address bits, and a label. So the data bits is the width of the register that this is representing, so it should be 16 bits. And the address bits basically denotes how many of those registers are in this register file here. So this is like a whole collection of registers. Now I would like to have 16-bit registers, and in order to address 16 registers, we need 4 address bits, because 2 to the 4th is 16. And then I'm gonna name that reg file. And like always, we need to have our clock signal brought over. Okay, so here's what the rest of these ports are for. So first of all, DN is a data input. So if we want to write data into one of the registers here, the data that will be written in is the data that's presented at DN. And RW is the index, that 4-bit index of the register that DN is going to be written into. And WE is write enable, so that's whether or not DN will be written to RW. So we have one input here, this DN input, which gets mapped to register RW. But then we have two outputs, DA and DB, data port A and data port B. And so these last two input ports down here, RA and RB, are the register indices that will be that identify the registers that will be outputted on the ports A and B, respectively. So if we put 0000 right here, then the first register, so register 0, it's whatever value it has will be output to data port A. And same thing applies to the RB and DB pair. So what I would like to be able to do is basically write a value from the instruction stream into one of the registers here, and then I think that's probably enough of a stopping point after that, because we're gonna have to do a little bit of work here with instruction decoding to establish what those instructions are going to look like in memory. So yeah, I'm gonna go ahead and cut this footage here, and then we're gonna swap over to Excel, and I'll give you a little bit of a look behind the curtain into where we're going instruction set wise, maybe. But then I'm gonna back off and just show you the simplified model that I guess we'll try to shoot for today, like at this very moment. Okay, so welcome to where the madness lies in all of this. So this is the currently planned instruction set. I'm sure some of it will evolve and adapt as we meet with the realities of implementing some of it, but I don't want to go into too much detail here, because I want to try to make current progress. But basically, if you're not familiar with this kind of thing, this is what is called an ISA, an instruction set architecture, and it defines the bit arrangements of instructions that the processor knows how to execute. And so there has to be like some information encoded in the 16 bits that the instructions are made up of. And so each of the columns from P over to A represent one of the 16-bit positions in an instruction. And so there has to be some number of bits in the instruction that are reserved as like an identifier for the type of operation that instruction is, and that's called the opcode. And so my instruction set is a little funny in that regard because I have variable width opcodes. So for this instruction right here, LUI, which is load upper immediate, this orange bit right here, 0, when an instruction has the value 0 and it's 15-bit, that means that the rest of this instruction can be interpreted as LUI. And the way that interpretation is going to work is it's going to know that bit 14 will contain a 1 or a 0 that represents the 14th bit of an immediate encoded in this instruction. And now this instruction has a bunch of different immediate bits. That's what all the yellow is. If you see the yellow in all these instructions, those are all immediate bits. So think about these as constant values encoded inside of the instruction. So, all of our values are going to be 16 bits wide because we have a 16-bit processor. But because the instructions are 16 bits wide, we don't have enough space to encode a 16-bit constant inside the instruction because some amount of space has to be reserved for the opcode. So you can see this LUI instruction encodes immediate bits 5 through 15, whereas immediate bits 0 through 4 are left unspecified. And it's up to the control logic of the processor to determine what those bits should be. Now, in the case of LUI, those bits are going to be hard-coded to 0. And the reason I describe that now is because we actually have like a couple different instructions here that are responsible for what I said that I wanted to achieve today, which is to load a value from memory into a register. Now, LUI, load upper immediate, is one of those. So the way that this instruction works is there's this 4-bit field here, and that is a 4-bit field used to index the register file. So this would be our RW, and our DN would be composed of this. So if we want to write the top like 11 bits or whatever of a register, we would use this. And similarly, we need another instruction or instructions for when we want to load non-zero values into the low bits of a register. So this is actually my first time looking at this in quite a while, but I think through here I have this instruction right here, which is load lower immediate. So you can see here it specifies immediate bits 0 through 4. So if we want to load the bottom 5 bits of a 16-bit value, or more precisely, a value that can be expressed in 5 bits into register RD, this is the instruction that we would use for that. So yeah, so what we're going to do today is we're actually going to implement this instruction right here. And so just know that there's a limitation on this instruction. We can only load values that are up to 5 bits wide into the register, which is, think about 5 bits. Like I said earlier, 4 bits allows you to specify 16 values. So 5 bits allows you to specify 32 values. So if we're talking about unsigned numbers here, this instruction can be used to load numbers 0 through 31 into a register. So yeah. So what we're going to do now is we're going to implement some stuff that is going to let us load or to interpret and properly execute LLI, load lower immediate. So I'm going to cut this here. We're going to jump back to digital, and I'm going to show you my plan for that. Okay, so I've drafted a little bit of a circuit up here in digital. It's not done yet. I figured I'd kind of try to like wrap up the last little part of it with you guys. But if you guys are not familiar with Ben Eater on YouTube, definitely go check him out. I think a lot of the people who are into the kind of things that I'm into right now are into it because of him. And so if you are familiar with Ben Eater, he's got his series for developing an 8-bit CPU like on breadboards, and it's very, very simple. But basically the control logic section of his CPU is implemented as a bunch of lookup tables, like using ROM chips, where the addresses on those ROM chips are like state inputs of the CPU. So his is not a single cycle CPU like mine is, but so he's got the instruction, he's got like a sequencer that identifies a step of the instruction, and he's got like the system flags, which allow like conditional execution. But then the output of that, like the data lines on the ROMs, is used as the control lines for the rest of the CPU. And this decoder unit right here is my equivalent to that. So basically the instruction is going to come in from the instruction register as we've previously designed it, and it's going to be the address on this decoder, and it's going to generate a bunch of control lines. So right now the only thing that we have to control is this register file. And so this kind of clues us into the type of control lines we need, because we know we need to have these RA and RB inputs, as well as the WE and the RW. But then the data input is interesting because, like I said, we're wanting to load an immediate into a register, and that immediate comes from the instruction. So rather than pulling the immediate out of this decoder here, since that would make it kind of potentially unnecessarily large since it's already in the instruction clear as day right here. I have this little branch right here that has pulled the 16 bits out right here. These 0 through 4 bits are RD, and 4 through 8 are the 5 low bits of the immediate. And so I'm going to plumb up those 5 bits there. So output bit should be 16. And then, yeah, so input we should have 5 and then 11 bits. Yeah. I'm going to see if I can mirror this. Say hello to Boomy in the background. He's getting the zoomies right now. So that means I need to get up and play with him here in a minute. But yeah, so that's our low 5 bits pulled straight from bit positions 4 through 8 of the instruction. And then these top 11 bits are going to be hard coded to 0. Yep, and then I might be able to clean this up if I do this. Yeah, great. Yeah, I don't actually need those 4 bits. Okay, so we're all plumbed up. So now, well, actually, no, we're not. So let's see. 4, 8, 12, 13. That's 13 bits here. Data bits, there needs to be, needs to be 13 bits there. And 13 bits there. Alright, it doesn't look like I have any wiring problems, which is cool. So, alright, next part is we need to put some data in this ROM that will appropriately set all these control lines based on the instruction in the instruction register. So I'm going to cut again, and I'm going to go play with Boomy for a little bit, but then we're going to get into VS Code and write a little bit of Python code to generate a binary for this. Okay, so welcome to VS Code. We're going to write a script that can take this encoding right here, which is the encoding for load, lower, immediate that you saw in Excel earlier, and it's going to basically be able to decode this and identify it as LLI and produce the appropriate control lines for use by the register file, but later the rest of the CPU as we kind of evolve it and grow it. So this script is going to start like pretty simple, but it will become more sophisticated. All the different colors and stuff that you saw in that Excel sheet is all going to correspond to enumerations and data classes and just additional logic in here to fully decode and model both the instruction set and the control logic inside of the CPU. But for now, I would just like to start with creating a simple data class that represents the control bus, which is what I'm going to call the set of control lines produced by the control unit, or by the decode ROM. So if you're not familiar with Python, this at right here means that this is a decorator, and a decorator can kind of be thought of as a sort of metaprogramming technique to either modify an existing class or function to attach additional functionality to it. And in this case, what the data class decorator does is it will automatically generate code to make a nice and easy to use constructor, repr method, and some other utility methods that just make your class easy to use and debug. If you're familiar with Python, you normally need to go in and write your dunder inits and take in all of your parameters and then manually create all your fields and assign them, and it's just like a lot of boilerplate. So the data class decorator is going to generate all of that for us. All we have to do is add some type annotated fields in here. So we know that we're going to need to call out RA and RB as well as RW, and each of these is the index for a register, and its type is going to be given by an enumeration we'll write here in a minute. And the last control line on the bus is this write enable line, which right now will just be true or false to denote whether we're going to write the immediate encoded in this instruction into the register file or not. But in the future, that immediate will actually be routed through the ALU, and we'll also be able to load values in from memory, like from data memory. And so this write enable will become some type of enumeration to select between not writing, or writing via a value from memory, or writing via a value produced from the ALU. And even further, if it's like a bytewise write or a full like 16-bit write or something to that effect. We'll get to all that like in later videos. But for now, we're just going to make it in Boolean because that's all we need for now. So another weird thing about Python is it doesn't have enums as like a language level feature. So just like how data class is this kind of like this decorator, and specifically the data class use of it is like a metaprogramming tool. This enum class actually has a custom meta class to it, which is going to make this class also kind of special in that when I create a member like this actually becomes like an enumerated value like you would find in a language with standard enumerations. So this is going to look a little weird to you if you're coming from most languages. So I'm just going to make 16 of these. I think that was 16. And then we're going to get rid of this. And if I understand the way that these enums work, I think these will just start to increment from 0. There's a decorator I can put here called unique, I think. And that will make sure that we never have any overlapping values in here. I'm going to go ahead and call this an integer enum since it's really just a collection of named constants. It's not like a Rust style enum or something like that that has extra data associated with it. So Python is a scripting language, so it's just going to start executing this file top to bottom, which means I could write like the main logic of this code like right in a global scope. Don't like doing that. It's a little messy. It doesn't scale well, especially if I ever wanted to import this file as a module somewhere else. So basically there's this special kind of runtime variable called _name that I don't want to go into too many details because this isn't a Python series, but basically this condition is only going to be true when you run this code directly as a script and not when it's imported as a module. So I'm going to use that to call this main function to make sure that the logic of the script only gets executed when we use it as a script and not when it's imported as a module. So now, because our instructions are 16 bits wide, we're going to iterate over every value that can be expressed in 16 bits because each of those values is a potentially legal instruction. Okay, so that's what that's going to look like. And then we're going to have an instruction called, a function called Decode instruction that will take that instruction in. And then we're going to basically collect a list of control words. And we're going to append like that. And actually, what we might as well do instead is use a list comprehension, which is kind of a more Pythonic approach for this kind of thing, where anytime you have an empty list and then you just have a loop that you just create a thing and add it to the list, that's usually a good candidate to make a list comprehension instead. Yeah. So the desired effect here is that we'll have 2 to the 16th decoded instructions. So I'm just going to assert that like expectation right here. And then now we're going to actually write the decode instruction function. Cool. So Python doesn't have like fixed width integer values. So unfortunately I can't just pass in like a 16-bit integer here and then just trust that, it can only ever be a legal value. Like this could be negative or this could be significantly larger than 2 to the 16th. So we're just going to assert here that the instruction is at least 0 and is no more than 2 to the 16th. So now working in here, we can treat this instruction as effectively an unsigned 16-bit integer, which is fantastic. So I'm going to basically pull the top nibble out of this instruction. Let me go ahead and pull this down here just so we can read it. So that's going to involve taking the instruction, shifting it down by 12 bits, and then just for cleanliness sake, we'll make it explicit that we only care about those bottom 4 bits. Even though when we shift down by 12 bits, those top 12 bits will now all be zeros that were shifted in. So we know that if nibble 3 is equal to 1111, then if these next 3 bits are zeros, then it's an LLI. Sorry, I'm trying to talk and think about how to write this at the same time. So we're going to do another kind of thing here and say nibble 2 is in. Yeah. Cool. So now we're going to pull out nibble 2, which are these bits. So instead of shifting down by 12, now we need to shift down by 8. And then we need to mask out these 4 bits, the bottom 4 bits, which is important now because there'll be 1s there. So because this is an immediate bit in the instruction, it could be a 0 or a 1, but it doesn't matter what it is, it's LLI if these top 3 bits are 0. So I'm saying if the top 4 bits are all 1s and the next 4 bits are either 0000 or 0001, then it's an LLI. And we'll write the logic for that in just a moment, but we're going to go ahead and produce the control word for all other cases for any instruction that isn't LLI. So for all intents and purposes, the only instruction we have right now is going to be LLI. So the only one that really matters in this case is write enable. It needs to be false. It doesn't matter what register indices we use for the others because as long as we don't enable write, no destructive changes to the system state can occur. But for cleanliness, I'm going to use R0 for all 3 of our register fields here. It's actually pretty hard to talk and type at the same time. And like I said, important part is that the write enable is disabled. Okay. So RA and RB, if I'm not mistaken, also don't matter. RW is the only one that matters for LLI with our particular hardware arrangement right now. So I'm going to go ahead and just make those R0s as well. And then RW is going to be the register identified by these 4 bits right here. So I'm going to make another variable here called nibble0, which doesn't need to be shifted down at all, but we do need to mask out the bottom 4 bits. And then while we're here, even though we don't need it right now, I'm going to go ahead and just grab the second nibble as well. Second nibble from the bottom. So nibble 0 is an integer, but we're going to convert it into a general purpose register so that we fulfill our data classes expectations. And then finally, write enable is going to be true because we do want to write this immediate into RW. And so that is that. So first of all, let me go ahead and run this. Boom, all of our assertions pass, which is great. Okay, so now we have a bunch of these control word objects, and we're now going to write them to a ROM. So I don't like the word ROM, it's just too generic in this case. But encode decoder also sounds a little weird, so I'm just going to roll with encode ROM instead. And we'll give it control words, and then we'll give it the name of the file that we want it to produce. Okay. And then just for simplicity, we're not going to return anything here. This will just be the end of the script. So now we're going to use what's called Python context manager. That's what this with statement introduced. And this is particularly useful whenever you have a managed resource. So a file, for example, is managed because you need to close it when you're done with it. And I could just use open as a function directly to receive this f file handle right here. But the problem is if this function raised an exception or something, it's possible that that file stays open, and so we get a resource leak. And we don't really need to worry about that in a batch program like this. But just for cleanliness sake, whenever you're working with files in Python, I do recommend that you use these context managers because it ensures that regardless of how this with block is left, whether it be cleanly or be an exception, that the file is clean and all your resources are released. So now we're going to iterate over all of the words in the ROM contents that we received. I actually don't like that name because it's not the content of the ROM, it's just the control words. And then just for giggles, I'm going to use named parameters down here because I do like that. It basically, that's the in source usage right here is kind of self-documenting. If this was thousands of lines of code and this function was really far away, it's nice to have the parameter names right here because it tells you what parameters each of the arguments refer to. So that's pretty cool. So now what we're going to do is we're just going to write each word to the file, but we need to convert it to bytes. So assume that this control words class has an encode method on it that's going to return an integer. And just so IntelliSense is happy, we'll go ahead and sub that out for now. Yep, so now we have 2 bytes. I think I made the output of the decoder, like in the simulator, like 13 bits. I'm going to bump that up to 16 though, since I can only write like in multiple of 8 bits. So I'm going to say that this has 2 bytes. I'd have to look at the circuit again to know what byte order to use here, but I'm just going to go ahead and guess a little. We'll find out soon enough if it needs to be big. And then it is not assigned value, which is the default, but I'll call it out here anyways. Okay. So now we need to take these 4 values and produce an integer out of it. So I don't recall if this is actually the order that the fields are in on the simulation, but we can come back and change this if that's not the case. So we're going to say self.ra.value. So whenever you have an enum in Python, the enumeration members have a .value field on them that retrieves whatever this is expanded to. So we need to bitwise OR all these together. And then we need to shift them as well. So I'm going to just say, okay, this is a Boolean, so it's 1 bit. So this needs to be shifted up by 1 bit. This is 4 bits, so that means this needs to be shifted up by 5 bits. And then that's 4 bits as well, so this needs to be shifted up by 9 bits. Okay, so let's run this. Cool, so that worked. So I'm going to cut here, and I'm going to load this decoder rom.bin in digital, and we're going to see what happens. All right, so if we right-click on this, we can click, not that, we go to advanced, yeah, so if we reload this at model start, make this ROM to program memory by an external ID. I don't think we need that. Reload at model start means that if we rerun that decoder script, we don't have to come in here and reload the ROM through here. It'll just automatically do it whenever it opens up. Yeah. So we'll select some of those. And let's see, like I said, that needs to be 16 bits. That needs to be 16 bits. And let's see what happens here. Okay, well, that reminds me. We need to have an assembler now so that we can produce instructions to put in here. So I'm going to code again, and we're going to create an assembler real fast. All right, so there's a really cool tool called Custom ASM. I'll try to remember to put a link to the GitHub project in the description of this video. But basically, it's a retargetable assembler, which means it's not like NASM or FASM, which are x86 assemblers, in that they're specially designed to interpret x86 assembly and produce x86 machine code. This is retargetable, so we can basically create our own assembly language and specify what the instructions need to be encoded as, which is really cool because it means that for projects like this, we don't need to put a bunch of elbow grease into writing an assembler right off the bat, because we can just kind of roll a quick and dirty one up with custom ASM. So for some reason, I've kind of been having an aversion to switching screens while recording, and so I haven't used custom ASM in a little bit. So we're going to see if I can remember how to use custom ASM just off the dome here. So basically, there's this rule def keyword, and anything in here is not like assembly code that will be output into a binary, but rather it tells the assembler how to interpret assembly code to put into the binary. So we're going to say LLI is the mnemonic, and we're going to do RD is going to be a register, which is a type we're going to have to go make, and then the immediate, which is going to be a 5-bit integer. So you can do U for unsigned, I or S for signed, or I for signed or unsigned, and we want to support signed or unsigned. And then this @ sign is like a concatenation operator, like left to right. And then we can do slices here. So this would just be 1 bit. I guess we're actually just going to go all the way down to 0 there by RD. Now RD, we're going to define using a subrule def. So the difference between a subrule def and a rule def is a rule def, you can just write this in your assembly code and it's going to encode it as an instruction, but a subrule def can only be used inside the definition of other instructions, like in a rule def or in another subrule def, which is good because I'm going to write something here like this. And I don't want someone to be able to write assembly and just be able to just write R0, like that's not an instruction. So basically what I'm doing here is essentially just creating an enumeration. Which I just realized I think I can just use decimal notation, which is going to be a lot easier for me to type out and a lot less awkward for you to watch. Let's see, 4, 5, 6, 7, 8, 9, 10. Okay, I think that is right. So do I have custom ASM set up here? I do, okay. So now we're going to make a file. We're going to call it test.asm. Go ahead and open this to the right. And then I think now I can just write LLI register 5 with the number 30 and see what happens. Oops, expected line break. Oh, okay, no commas. Okay, is there an easier way to do that? I think I can do this. Yeah. All right, so let's open up this binary. That is not what I wanted. Let's see, do I have a hex editor? Okay, so let's look at this a little bit more closely. Got 1, 2, 3, 4, 5, 6, 7, 8. 6, 7, 8. Okay, cool. If we pull up the decoder.py, we should have 1, 1, 1, 1, and then 0, 0, 0, 1, and then let's see. That would be register 5, right? 0, 1, 0, 1. So I think that is a correct encoding. Now the problem is going to be now. that this is one ROM, but the simulation is expecting 2 ROMs. So let's jump back to digital, and we'll rework that a little bit just for now until I figure out how to use custom ASM a little bit better. Okay, so we're gonna replace the 2 ROMs with just 1, and I don't think that's gonna really cause me any problems, but watch it cause me all the problems, really. I do want to point out in the future, when the CPU is a little bit further along, this is not going to be a Harvard architecture processor. It's going to be von Neumann. So this one ROM will be a bit more complicated to interface with because access to it needs to be mediated, since the memory stage further down the pipeline will also be trying to use it. Okay. Okay, test.bin. Alright, what's going to happen here? Is this going to work? It did something. Except it didn't. Where's our value? Alright, I'm going to cut here and do a little bit of debugging because I'm a little lost in the sauce. Alright, I'm back, and I added a few signals here to help kind of demonstrate what's happening a little bit. So if you recall, we wrote a small program that all it should do is load the immediate value 30 into register R5. So if I start the simulation here and I clock us once, you'll see that the instruction in the instruction register is what we saw in the hex editor in VS Code, F1E5. And you'll see that, I guess by happenstance, I did happen to just get the little endian and the encoding order correctly in the Decode script, because we've got our write enable signal enabled. Our RW is register 5, and then our A and B are 0. It's possible those are backwards because I made them both 0 in the script, but that's okay. So yeah, very, very little to look at, but we kind of got a lot going in this video, really. I kind of stumbled through this, but you know, we fetched an instruction from memory and loaded it into the instruction register. That instruction in memory was created via an assembler we now have, and then it was decoded and translated into stuff that actually happened over here. Which I guess let's clock again. Yeah, was that there? Was I missing that? Hold on. So register 5 is 0. Register 5 is 0. Down clock. Reclock. X1E. Okay. Anyways, like I said, stumbled through this. That might have been one too many clocks. I might have intended that to show up 1 clock earlier than it happened to, but also this viewer might be like buffered by like a clock cycle or something. I honestly don't really know. I'm not very smart. But anyways, that is that's all I wanted to have happen in this video, and there were a couple steps in there that I totally forgot that we would have to whip out in this video, like the assembler, but that came together pretty easily. Again, I'll link custom ASM in the description, and I'll also link digital, which is this software we're looking at right now. But with that, thanks for watching. I'll work on stitching these clips together and get this out to you guys, and then start working on the next part, which is hopefully potentially going to be like an adder, perhaps. So like the very initial parts of an ALU. But with that, I'll catch you guys in the next video.